Okay, let me introduce the first invited speaker, Dmitry Mordvinov. Dmitry is a researcher at JetBrains Research and senior lecturer at St. Petersburg State University. He leads the formal verification group in JetBrains Research. His research interests include software verification, symbolic execution, type theory, and model theory. So, Dmitry, you're welcome.
Thank you very much. So, as was said, I'm Dmitry. I'm the leading researcher at PLT Lab of JetBrains Research, and it's really a great honor to give a starting talk here at CIRCOS in Higher School of Economics. So my talk would be about the symbolic execution, and it will consist of two parts. The first part will be an introduction level tutorial about the symbolic execution. And in the second part, I will try to briefly discuss our advances in this field. So, imagine that you are a machine. Look at this function. And imagine that you know nothing about the formal specification of this function. In other words, forget everything that you know about the absolute value of a number. Now, the question is, what will you consider to be a good test coverage for this function? And well, we have a pretty standard answer for that, and it is connected with some code coverage metrics. For instance, the idea is to look at different parts of the programs and see which parts are covered by the tests. And those parts can be statements or instructions, and in this case, we talk about the statement coverage. Or they may be branches or edges of control flow graph, they may be functions, and so on. And in this concrete case, for example, we can just take these two tests and they will exhaustively cover every branch in this program. So we can consider these two tests to be a good test coverage for this function. But really lots of questions arise. For instance, which coverage metrics is the best? And how to test, how to measure test coverage of the concurrent code. By the way, tomorrow, my colleague Anton Podkopayev will be giving a talk about the concurrency. He will discuss the so-called weak behaviors of concurrent programs, and probably will see that the situation is even worse than you might have expected. Or vice versa, I don't know. So what if we have some distributed system with some complex interactions between the components? These are three questions that will not be covered in this talk. They're a bit beyond this talk. But actually, there are some other interesting questions that we will partially cover. For instance, how to reason about the code, about the recursive code that has potentially unbounded amount of behaviors. Or how to guarantee that we did not miss some critical interactions of the program. For instance, does anybody recognize this code? This is a pretty famous snippet. Well, okay, this is the snippet from the...
It's a heartbeat vulnerability, right?
Yeah, that is. So this is a snippet from the TLS heartbeat extension implemented at OpenSSL. The thing is that it has a vulnerability, and it is in this concrete line. This is a very famous one. It is called heartbleed. So here we fill in the response buffer, and we copy the information from this PL buffer. But the thing is that we use this payload parameter that is input, and it is not validated in any way. So here we can, this is a typical buffer overread situation where we can read too much. For instance, we can read the whole buffer and the whole process memory allocated after this buffer. So the question is how to guarantee that we do not miss something like that when testing the function. And the most important question that we will start discussing right now is who will write all these tests? So maybe you have a standard answer for that, testers of course, but I will try to talk about some other idea. Let me say an academical dream that we fire all the testers and let the machine assist us in this process. So let the machine generate all the tests by themselves. So we have this test generation problem where we're given a program and some code coverage metrics, and our task is to automatically generate the exhaustive test coverage of this program with respect to a matrix. But of course, it is a bit idealistic statement. Here we are given all the time in the universe. The more realistic statement is we're given a program, we're given metrics, and we should maximize the coverage of the code within some time limits. Now, this is a formally stated problem, and we have some approaches already for this problem. And usually we classify them in three categories. The first one is, so this is black box, gray box, and white box approaches. And the black box approaches know nothing about what happens inside the program. Instead, they observe only some external things like program output, like crashes, like if the program does not terminate in some time limit, and so on. And one mainstream approach here is fuzz testing, or simply fuzzing. So fuzz testing is just the incarnation of the idea where you get 1 million of monkeys and give each monkey a keyboard. So of course, the monkey will generate random inputs for our application, and probably some monkeys will guess the right inputs that will discover some interesting program behaviors. So there is one there is one example of pretty successful black box fuzzer. This is a reductor fuzzer written by Daniel Stepanov from JetBrains research. This fuzzer tests random, this fuzzer generates random programs and give it to Kotlin compiler, and they've managed to discover a pretty number of bugs in different backends. Now, there is gray box fuzzing approaches. So the idea is that we take the program code and instrument it in such a way that we know which branches are taken by this concrete input. And then we can use this information to encourage monkeys that started generating right inputs. And the very famous example of gray box fuzzer is FL. And we have this white box approach where we have full information about our program, and we let the testing system infer the test values instead of guessing it. So nowadays, I would say that white box fuzzing is almost synonymous to symbolic execution. And let's discuss what is it. Well, I think that the best way to explain what is symbolic execution is just to show the example. So here again, we have this absolute value program, but written in some different way to simplify it. And also we have this part that validates that the absolute value is non-negative. So here we have already some formal specification for this. And our problem, our task is to generate tests that exhaustively cover every possible behavior of this program. And in fuzzing, for instance, we would generate some random values and try this program, where in symbolic execution, our idea is to represent every possible value that X can take with some superposition of concrete values. And this abstraction is called symbol. So we're just writing a symbol into the location of, into the variable X, and thus non-deterministically investigate different behaviors of this program. So as an usual interpretation of stated programs, here we have state as well. It is called symbolic state. So what is symbolic state? The symbolic state is a triple. The first element is the instruction to be executed next. The second element is the memory of our program, but it may contain the symbolic values instead of concrete. That's why we call it symbolic memory. This is the second element. And the third element is so-called path condition. Well, path condition is a formula, and it represents the states that could drive us into the current branch which we are currently executing. So initially, our state is the first instruction of this program, writing 0 into ABS. And initially, the memory is filled with something. It's filled with some non-deterministic values. Again, we represent the non-deterministic values with symbols. So let's say that variable ABS contains symbol A, and variable X contains symbol X. And of course, we always can reach the starting branch. If we started the program, we're already at this instruction. So our path condition is just a formula true. So we can, if we already started the execution, we already got into this branch. Now let us execute the first instruction, is writing 0 into the ABS location. And this will do what you expect. We'll just write 0 into our memory. So here we get the state where 0 is written into ABS, but X is unchanged. And we transition to the next instruction. This instruction is the conditional statement. Here we must first evaluate the condition itself. The condition is X is greater than 0. To evaluate it, we must first read X. So we just look into our memory and see that location X contains this symbol X. And then we just execute this expression on the symbol. What we get in the result, we get the symbolic expression X is greater than 0. So now it is the result of the evaluation is just a formula. And here the execution goes in a bit different way than the normal execution. Here we try to investigate both branches. So for instance, we investigate the then branch by conjoining the path condition X is greater than 0, so it is the condition that was evaluated right here. And we investigate the second branch, else branch, by conjoining the negation of this condition. And the state is not modified because the evaluation of the statement will not modify the memory in any way. And then then something very important happens. Our execution has forked. So we have 2 branches instead of 1, and now our task is to understand if these branches are reachable. So our condition can be unsatisfiable, and we should check it if it has some concrete values that will drive us into this branch. For this, we use some kind of oracle. Usually we call this oracle solvers. And let us imagine that we have some magic solver that takes as input the system of these symbolic constraints, and as output it tells that these constraints are satisfiable and gives us the concrete inputs that will satisfy this constraint, or say that they're unsatisfiable. So if we have such oracle, we ask him if every path condition of forked branch is satisfiable. So here, for example, our solver says that, of course, we have some positive number, for instance, 1. And this already can be a test input that drives us into this branch. So by just one query to a solver, we have already discovered one input that drives, that covers half of the initial ABS program. Then we ask the same thing about the second constraint. And of course, it says that we have non-positive numbers, for instance, 0. And again, we have discovered the second input. So we have already covered 2 branches of the ABS just by querying just by giving 2 queries to a solver. But now we have this validation property that ABS is always non-negative. So let's proceed our execution and see what happens. Now we should execute these 2 instructions. So first we write X into the ABS, and it will do what you expect. It reads X from the memory and writes it into the ABS location. And then we evaluate this condition if ABS is less than 0, and it will give us the constraint X is less than 0. And we can join it again to a path condition. We obtain this symbolic constraint. This is the conjunction that says that X is positive and it is negative. And of course, the solver will say that this condition is unsatisfiable. We don't have positive and negative number at the time. So we have managed to prove that the assertion that this fail instruction is unreachable. Now, this is the second part that we can achieve in our symbolic execution. We can prove that some branches are unreachable. And let's see what happens in the second branch. So here we evaluate the ABS. We write -X into the ABS, so we get this state where ABS contains this symbolic expression -X. And then we read the result this result from ABS and say that it is less than 0. So we can join the constraint minus x is less than 0 to our path condition. Now, again, we query the solver if this path constraint is satisfiable. And how do you think, what is the answer? So this constraint says that x is not positive, and this says that minus x is negative, so you might think that x is positive. So here again, we obtain two constraints, x is not positive and x is positive, but it is satisfiable. So there is one case where this minus x might overflow, and we get this complex, we get this input x is equal to the minimal integer, which drives us into this branch where we fail. So actually, we have managed to infer a very thin path, which uses some complex overflow, where we have the complex overflow behavior. And one thing that I want to say here, and imagine that we use fuzzers for this particular input. So it might happen that the fuzzer makes 4 billion randomizing attempts and still it will not discover this input. While here we have asked only 4 queries to a solver and exhaustively explored all the program behaviors. And this is what the symbolic execution is. So this is a technique of systematical enumeration of all program paths, formulating the so-called symbolic constraints for each path, and then asking the solver to give us the concrete inputs that drive our program to this path or try to prove that this path is unreachable. Okay, so with this thing in hands, we can achieve really many things. For instance, we can find bugs in programs, automatically find bugs. We could even sometimes prove the correctness of the program by enumerating every possible behavior of the program. We can automatically generate test coverage. So this is our case. This is our problem that we are discussing. We can look for safety vulnerabilities and even automatically generate some exploits. And there are other interesting applications like smart debugging, where the debugger leads us to the program branch of interest itself, or code profiling, so we can improve the performance profiling by using some techniques in symbolic execution and so on. We have papers for each of these applications, and I will share you if you ask me. Well, there are some academical achievements, not academical, even practical achievements of symbolic execution. So these are 3 that pop up into my mind immediately. I'm sure that some experts in symbolic execution can tell much more about these achievements. So for instance, there was a SAGE symbolic execution engine written in Microsoft Research, and it managed to find 1/3 of all automatically discovered bugs in some applications developed during the development of Windows 7. We have this merge point cluster that have managed to find almost 12,000 bugs in different Debian binaries. And we have this S2E tool that that played the CTF challenge with humans. Well, the CTF challenge is the capture the flag challenge of hackers. So there are hacker teams, they get some services, and those services contain vulnerabilities, and the task is to find these vulnerabilities, to fix them, and to write exploits to steal points from other teams. Well, S2E managed to play completely automatically, this change completely automatically. Yeah, so that symbolic execution has appeared back to 1976, and these achievements are 2008, 2015, and so on. So almost 40 years have passed, and you may wonder why. Why didn't we have such achievements before? And I would say that the reason is some breakthroughs in the constraint solving. So I will not focus on this topic a lot because it is really large. Instead, I will say that the problem of automatical constraint solving is connected to some NP-complete problems that were, and just in 2000s, we have got some still exponential but efficient in practice algorithms that can address this constraint solving problem. And now we have very efficient tools called the SMT solvers. So SMT is satisfiability modular theory. So they check the satisfiability of the first order formulas. In some theories, those theories can be the theory of machine integers, or like we say bit vectors. They can be the theory of arrays, algebraic data types, strings, and whatever you have in programming. So you can formulate these constraints in terms of machine calculation and automatically find models of such constraint. The model is just evaluation of all symbols in these constraints, or even proof that this constraint is unsatisfiable. Now, of course, we have the efficient in practice algorithm, but still, SMT solvers are the bottleneck of symbolic execution engines. So that's why they require the accurate management of the symbolic constraint. The symbolic engine should simplify the constraint as it can to simplify the further solution by the SMT solvers. And we have pretty bunch of techniques here. For instance, we have some techniques of minimizing the formulas using BDD or some DPLL integrated techniques. We have some constraint slicing and independence technique. Well, we tried to split the constraints into the independent groups and solve them in a faster way, like implemented, for instance, in CEDAR engine. The implied value concretization implemented in klee. We might cache models returned by solvers to speed up the subsequent solver queries. And we can pass the constraints into the SMT solver in some incremental manner. What means incremental? So if usually in program, if you investigate some branch, you can join here, for instance, we have conjoined the path constraint to the existing path condition. But here we have already solved this x greater than 0 condition. So if we go pretty deep, we can already have a bunch of path constraints, and we have already solved them, and we can join just one of them. So we don't want to resolve all the constraints we have already solved once again. And this is an incremental manner. So you just, if you can join one path constraint, you just want to solve this particular constraint within the conditions of other path constraints. So we have the techniques implemented in different symbolic virtual machines. Yeah, so this was the problem of constraints management, and it is important. But yet more important is this problem of path explosion. And it is connected with the combinatorial property of the branches of the program. So if the symbolic execution machine execute this conditional statement, it forks every state. So for instance, if we were in this state, in the result, after executing this statement, we get 2 states. But imagine that we do this conditional execution in loop. So we iterate this condition n times, and in the result, each state forks twice, then it forks twice again, and again. In result, we may obtain exponential number of branches to discover. So this property, when the amount of path grows exponentially within the number of iterations of unrolled in the loop, is called the path explosion problems. We have one small code sample which gives us the exponential amount of branches. And yeah, so there is even another problem connected with it. Yes, so this is the path explosion problem, and we want to address it somehow. And the usual approach here is to prioritize states in some way. So if we can't enumerate all paths, let's enumerate the important paths first, and then look to less important states. So the typical algorithm of symbolic execution will look like this. So this is the algorithm that I have seen in almost every symbolic execution machine I've ever seen. So this is how the pseudocode of how looks the main function of every symbolic execution engine. So here we start with one starting state, entry point of the program, and we place the state into the queue. The queue is just a set of states, and then we pick the next state, we delete it from our set, and forward propagate it. So we just execute the instruction on this state. We get in result some, this state might have been forked. And for each fork, we just check that its path condition is satisfiable and can join this state to our set. And here, these search strategies are usually implemented in this searcher object. So it takes as input the set of the currently investigated states, and it picks some state using some heuristics. And those searches might be pretty standard, like deep first searcher or breadth first searcher or iterative deepening searcher. But also we have some more sophisticated techniques like weighted random searches. So we randomize our search using some weights on the states. Or we can use some coverage optimized search when we pick a pair of state and an uncovered target of the minimal distance with the minimal distance and drive the state which is the closest to one uncovered target. Or we might interleave some searchers and so on. Oh, this is the typical approach which we apply for solving the path explosion problem. But still, if you execute some loop with symbolic exit condition, for instance, in this loop here, if n is symbolic, we just obtain those conditions. 0 is less than n, then 1 is less than n, then 2 is less than n, and we never might be sure that this loop has terminated because we don't know what n is. So in result, we get the avalanche of states, which when we propagate each state, again, we obtain some states, and some of them has left in the loop, and we should propagate them again and again and again. In the result, we get this exponential amount of states, and we want somehow to control the size of this avalanche. And this is performed by introducing the artificial bound on a number of iterations that symbolic execution engine might take. The idea is just to control, to calculate the number of iterations that some state, the path corresponding to some state has made. And this is the so-called level of the state. And if this level has exceeded the bound, then we just stop exploring this state. So we don't care about the iterations that are beyond our bound. We are bounding the symbolic execution artificially. Of course, there are other ingredients of symbolic execution. For instance, lazy instantiation, function summarization, and these two techniques we will discuss right now. But also we have, let's say, some advanced topic in symbolic execution. For instance, mixing the concrete and symbolic execution to speed up it. We have some techniques of merging states at control flow joint points to minimize the amount of the explored states. We have some memory models to handle the pointers in program in smart way. And we also have some techniques that explore the interaction with the environment. This is another problem of symbolic execution. If you execute the code that makes has some foreign function interface, the external call, if it calls the function that you cannot symbolically execute for some reason, then we should think about something smart here. So our code is calling functions that we don't know what it's doing. So we can't apply those white box techniques anymore. So we should somehow combine with black boxes approach and so on. But right now, I will talk about two techniques that matter in my future talk, in the future part of my talk. And this is lazy instantiation and function summarization. Well, what is lazy initialization? This is the technique that was proposed in the paper here. So this is a technique that allows us to support programs with pointers in symbolic execution. So for instance, here we might have the program that traverses some linked list structure, and we can have some symbolic pointer. And you may ask what to do if we indirect some symbolic pointer. So this paper gives an answer. The idea is to instantiate new location and tell that this pointer references this location. But before instantiating this location, we must consider every case that this pointer aliases some already known location. So how it would work in this example? If, for example, we got the symbolic pointer next, then the symbolic pointer this, in this case, this is a Java code. So we don't know what is this, but we simply instantiate the object for that. And we say that its content is symbolic. We just instantiate an object in the memory in our heap with a symbolic address and consider its content completely symbolic. So again, if we read this field next, we again get the symbolic pointer, and then we consider two cases where this pointer references already allocated location. So in this case, we have a south loop in the list, or it references some new location with, again, unknown content, and so on. If we unroll, for instance, some loop that traverses this list, we'll consider every possible linked list with the non-deterministic content, and it will be instantiated just up to the amount of the iterations that this loop will do. So this is the idea behind the lazy initialization. Another technique is function summarization, and it is a technique where we generate some first-order formulas that summarize somehow the parts of our behavior of our program. So for instance, we may generate the formula that somehow describes the relation between inputs and outputs of the function. Here again, our ABS example. And if we have called ABS on some random number, and then we want to validate that this ABS is positive, and if we have already previously executed ABS, we might have generated some formula. So this is the idea behind the summarization. If we have already called this function, we may reuse the results in the form of the condition to speed up the analysis at this time. So actually, we just over-approximate the function with some formula, and this is one of the examples how we could do it. It is so-called disjunctive summary, where we just unify with the disjunction different function, already investigated function behaviors. So for instance, in this case, we might say that ABS is over-approximated by this behavior, by this formula, where if x is greater than 0, then the result is x, otherwise the result is minus x. And actually, it exhaustively describes the behavior of our function, so it is not a very interesting summary. Instead, there are techniques of generalizing these summaries. So the idea is to simplify the formula by over-approximating it. So what's the problem? The problem is that the function has a lot of paths, and such disjunctive summaries might be first expensive to check, and loop and recursive functions have even potentially unbounded amount of behaviors, so we'll even never exhaust such behaviors with such disjunctive summaries. So in this case, we could over-approximate this summary by some, for instance, this formula. We say that ABS is non-negative if and only if x is not the minimal integers. So we have some techniques for automated generalization of such summaries. So this summary 2 is coarser than summary 1. What means coarser? So it over-approximates. It is implied by summary 1. An implication in logic is just like the subset in the set theory. So we say that the set of states described by summary 1 is the subset of states described by summary 2. So summary 2 is a bit coarser, but it is simpler summary of this function. And we have some techniques for generalizing such summaries. For instance, unsat course, if we have some unsatisfiable result, we might automatically try to extract the minimal unsatisfiable subset of this conjunction. So, for instance, it might be A1 and A3, and then we might say that our new summary is A1 and A3, and it is coarser because it is implied by this big conjunction. So if we have more conjuncts, then the conjunction is applied, but not vice versa. We may have Craig interpolation techniques, and it's a very curious one. The first order logic possesses this very important Craig interpolation property, where we, if we have two formulas and their conjunction is unsatisfiable, then we have some first order formula that it consists of only of common to these two symbols, and it over approximates our formula A, and it is still strong enough to be unsatisfiable with B. So here, this interpolant, Craig interpolant, like we say, I, is over approximating our summary A. So this is another technique how we could automatically get those generalizations. I should say that if we use SMT solvers and if we get some unsatisfiability result, the SMT solvers produce the unsatisfiability proofs. So if we have some unsatisfiability result, we already have the unsatisfiability proof. And these two things are just, you can obtain them almost for free if you have the unsatisfiability proof. So these two techniques allow us generalizing the summaries almost for free. There are other examples of generalization. One famous one is the inductive generalization in IC3 and so on. I will not talk too much about this. Now it's time to demonstrate something that works. And in this work, we have used the engine called klee. So klee is a symbolic virtual machine for LLVM. It is open source, and it has some simplification, constraint simplification heuristics implemented in it. It has various path selection strategies like random weighted search or deep first search. It uses the incremental constraint solving and supports a bunch of SMT solvers, including Z3, their own SMT solver, STP, and Meta SMT protocol. So they have implemented the segmented memory model. So this is some advanced knowledge for experts. They model memory with arrays and bit vectors, and they concretize addresses and size of the blocks. So they do not have the blocks of symbolic size or symbolic addresses. Instead, they just under-approximate the behaviors, but still stay efficient. They have implemented some state merging heuristics, and they concretize the state by the solver to handle the external functions. So let me show this klee in action. Here I have this example. This is a standard example from the website of klee. You may download this file. This is a simple regular expression matching engine from the book Practice of Programming by these two authors. Now here we have this test harness where we make some symbolic buffer. So here we have some buffer of size 7, and we fill it with some non-deterministic values. So here, this is the way how we make the symbolic values in klee. We just include some klee header and tell that the contents of the buffer is symbolic. And now we just try to enumerate some regular expression patterns that will match the string hello. And our task is to cover this matching engine. So here, so this is some recursive function, Loopian recursive function, mutually recursive function. So our problem is to generate some patterns that exhaustively enumerate every path, every possible path that this engine might take. So we may run klee and see what happens. Yeah. First, of course, we must compile this example. I will do it by compile it with Clang with some recommended options. And then I just start klee. On the obtained bytecode. So it has managed to detect some errors in this code. And we'll wait, I think, 5 more seconds. well, yeah. So klee managed to cover every path. So let's see, klee stats. We have this tool called klee stats that shows what just happened. So here we have some, let me decrease the size of the font. Yeah. So here we have some detailed statistics of what just happened in the last run. So this is the amount of the instructions executed by the engines. This is the time taken by the engine. And this is the resulting coverage. So klee has managed to infer the test that exhaustively cover every instruction and every branch of this program. And the time taken by the SMT solver is 24%. We may even look at these inputs. Let me do it in this way. So here we have some test cases, and these are patterns that klee has managed to infer. I guess it is not so readable because it is binary. Well, okay, so it has managed to infer some patterns like these caps with H. For instance, the beginning of the string H and then hello here. So some input data that exhaustively covers this regular expression matching engine. So, and this is the end of the first part of my talk, the tutorial part. And now I will try, if you have some questions, you may ask it right now, because now we are going to move to the second part where I will try to discuss our own research in this topic. Again, let's roll back a little bit. We have discussed this test generation problem where we had a program and some time limits, and we should have maximized the test coverage of the program with respect to some metrics. Now, I will discuss slightly different statement, a slightly different problem. Here we have the problem of targeted test generation, where we are given the program and a set of control locations of this program that we must cover as fast as possible. Of course, it is a bit more general statement because the usual test generation problem, here we could just give the interesting parts of this program, the statements or all branches of the targets at the begin of all basic blocks. But actually it turns out that it is not so investigated problem in literature yet. But still it is very important because it has some interesting applications. For instance, here we might notice this suspicious pattern in the code, and we might ask to witness, to infer the branch where something bad happens. So here we can just focus this line memcopy with some additional requirements. And if we have some targeted test generation engine, then we will quickly find some test inputs that lead us to bad behaviors of the program. So some targeted bug finding or exploit generation is one prospect of application. Another prospect is an integrated development environment button cover these lines. We just can right-click some line and ask the test generator to generate the unit test that leads us specifically to this line. Or maybe we could even speed up the regular test generation by focusing the uncovered blocks and trying to quickly find paths that lead to these uncovered blocks. So if we interleave this targeted generation and regular generation mode, maybe we could obtain some profit from this targeted test generation engine. So how to solve this targeted test generation problem? Well, there are two ways. One way is just to use the casual symbolic execution. We just run the symbolic virtual machine and we pray that our targets get covered. But of course, this approach is a little bit too much here. So this is like taking fuzzer and praying that it guesses the right input. And there is a second approach, a smarter approach, where we develop some targeted symbolic execution engine. And People have developed some approaches to backward symbolic execution. The idea is that you get the target as the starting point, and then you just execute the program back, trying to reach the entry point of the program, the main function. And it sounds pretty attractive, but the problem is that it still explodes. So the backward execution still must fork. Now it forks at control flow graph joint points instead of the forks of the control flow graph. So if you have the loop, of course it has some entry point, and each entry point will be a fork. So we can have two input edges into every loop, the beginning of the loop and the backward edge into this loop. So it still explodes in the loops, but even more major problem is that we need to consider now when we reach the entry point of some function to backward propagate from this entry point, we should consider every possible call site of this function in the program. And there may be quite a number of such. So backward symbolic execution still explodes, and it is not the ideal solution for this targeted problem. Our idea is try to combine the forward and backward symbolic execution, and we call it bidirectional symbolic execution. And the intuition here is easy. So the program is like a large maze where you can have an entry point, for instance, this home, and you can have some targets. You have some exits from this maze. And well, I think everybody who tried to solve mazes has done, like they have taken the exit and lead the line from the exit. And if the maze is simple enough, then you quickly approach the entry of the maze. But of course, you can still explode by exploring the wrong directions in this maze. The idea is just try to lead two lines, one from the beginning and the second from the end, and maybe they will conjoin somewhere in the middle. So this is essentially what we make. We have two ideas here. These are two core ideas. So one idea is to maintain a set of so-called proof obligations, or just POPs. This is the term that we borrowed from the software verification domain. So what is a proof obligation? It is just a triple where the first element is the program location. The second is a level, so this is the amount of iterations that somehow bounded to this proof obligation. And the third element is just a first order formula. So this is just a constraint of this proof obligation. Initially, when we get the targeted test generation problem, we initialize POPs with this triple, where we enumerate every target and just bind this POP to the target location, allowing to make the maximal amount of steps possible, and the formula is just true. So we must reach this location no matter with what conditions. So this is the first idea. Maintain this set of proof obligations and propagate this. And the second core idea is to perform the search in two directions, forward and backward. So now we have two queues, queue front and queue back instead of one queue. Here and perform two steps. The forward step is just the regular symbolic execution. So if we have picked some state from queue front, we might execute this instruction. Of course, the state might fork, and we place the result of each fork after checking its satisfiability, like in regular symbolic execution. And the second step is the backward. So here we apply some techniques from the so-called symbolic reachability analysis. So the idea is to store these proof obligations into the second queue back, and we propagate proof obligations instead of states by iteratively computing their so-called weakest liberal preconditions. So if we have some state that has approached the proof obligation, then we might backward propagate this proof obligation to the beginning point of this state. So as you can see, here already we have some insights that we should obtain states from the middle of the program. If somehow we manage to symbolically execute the program from the middle and approach the proof obligation, we might backward propagate this proof obligation back to the starting point of this state through one concrete branch. And the third idea is to execute code fragments in isolation, and you reuse the obtained symbolic states for both forward and backward propagation. So the obtained states will speed up both propagations, optimizing our bidirectional symbolic execution a lot. And to achieve this, we must use some advanced techniques. One of them is, for instance, the discussed technique of lazy instantiation. So this is the technique that will allow us executing code in isolation. And if we use such approach, we have no need to write the backward symbolic interpreter, just like the reversing the semantics of every instruction. We may just reuse the code base of the existing symbolic virtual machines. And also, by executing code in isolation, we may obtain some form of so-called compositional reasoning. What is the compositional reasoning? So the idea of compositional analysis is when you just analyze the parts of the programs in isolation, and then just combines the analysis results to obtain some knowledge about the whole system. So this is like the divide and conquer approach in the analysis. In the result, we obtain some compact representation of states and path conditions, which are not so large if we execute the program from the entry point and try to reach our targets. Now, my talk will be a bit too technical, maybe. So now I will show how we execute the code in isolation. As I've already said, it is connected to this lazy initialization technique. Here, if we have some state and if we have some function, we might not expect the call size of this function. We may execute it in isolation by taking the non-deterministic values of its parameters, and we might have the pointer here. And the idea is to use this lazy instantiation technique. So how does it work in more detail? So here we have a function that checks that the pointer is non-null, and then it writes the field X of this structure A into the field Y, and it returns the result on this right. So another branch, if A is null, we return just -1. So here, the first statement is this branching, this conditional statement. So here we just evaluate A. So this symbolic memory. So the idea is that we take an empty symbolic memory, and if we don't have a location for some interesting variable or heap block, then we just instantiate it. So here we read the pointer A, and we don't have an entry in the symbolic state. So we will instantiate it by evaluating it to some LE expression. So we just memorize which locations were instantiated, and as the result we get this path condition that this lazy instantiation of A is not equal to 0. And in the second branch, we have this, when it is 0, we just execute return -1 and finish. So in this branch, we want to execute this statement read AX, and the result that we get is this one. So this is lazy instantiating the field X of lazy instantiation A. So lazy instantiation of A gives us the value of the pointer, then we shift it to the field X and lazy instantiate it again. And here we have read some heap block that did not exist in our memory. So here we instantiated this block, but fill it with, again, uninitialized content. And here we want to write the result of this evaluation into the field Y. So we just perform this write and obtain this state where lazy instantiation A references the structure where the field Y contains the result of the previous evaluation. Yeah, and this is the result of both branches. So this code will be evaluated in isolation to these two terms. Now, this is the first ingredient of our approach. So the second ingredient is computation of weakest liberal precondition. This is a pretty standard thing. What is the weakest liberal precondition? If you have a program and you have some formula which expresses the so-called postcondition, I mean, this is a formula that represents a set of final states of the program. Then the weakest liberal precondition of this formula with respect to a program is just a formula, the weakest possible formula, such that every state satisfying P, if the program starts in these states and terminates, then the resulting states should satisfy Q. So this is a pretty standard thing, book stuff. And let me show how it works with this small example. If we have the program that just increases x with 1, and we have this post condition x, so here we ask, what should we require from x to obtain this property that after execution this program we get the formula, we get the property that x is greater than 10. Well, you can do it by substituting the right side of this assignment. So here we have this, the implicit assignment x is x plus 1. So we substitute x plus 1 into this expression and we get the required result. So x is greater than 10 after increasing its value, only if x was greater than 9 before increasing this value. So this is the weakest liberal precondition, and the intuition here that this is essentially the notion that allows us rolling back the proof obligations through the code. And our contribution is the new formulation of this weakest liberal precondition by exploiting the results of this symbolic execution. So if we compute the weakest liberal precondition like this, we just, if we recursively replace every lazy instantiated allocation in the formula Q by reading these results in the state S and then conjoin the past condition of the state, we actually obtain the correct weakest liberal precondition, which possesses two good properties. First, it allows to compute the weakest liberal precondition through the individual path instead of the whole code like we obtain in some weakest liberal precondition evaluations like in, for example, higher logic. And the second one, that this lazy instantiation approach allows us to consider correct cases of the aliasing, of the pointer aliasing. So for instance, here we have two pointers and we have a code that writes x into the pointer p and then writes 1 into the field x of the location referenced by pointer p, and then it writes 2 to the same field of the pointer q. And we fail if the results that stored in those two fields are equal. So this fail, of course, might happen if P and Q reference the same location. So if these two pointers are identical, then we get this fail. And within this formulation of the weakest liberal precondition with lazy instantiations, we actually get the correct formulation of the VLP through this code. So actually, if we compute the VLP of this condition, we will evaluate it to the quality property of two pointers. This is one nice thing. Now we're ready to describe our bidirectional symbolic execution algorithm. So here we maintain, as we have already told, two sets of Q front and Q back. Q front is a set of states, and Q back is a set of targets. And now we have a bit another workflow of our work. We still have some flexible search strategy. So we still have some searcher, but now it is parameterized by two sets. One set is Q front and the second is Q back, and it makes its decision looking towards the results of these two, looking at the states of these two sets. So the searcher might take three decisions. It might start some new exploration from somewhere from the middle of the program, or from the entry point of the program. And then it can go into two directions. The first direction is go front, and the second is go back. So if we start the exploration from some point S, then we just conjoin our state S into the Q front, and then we will forward propagate the state. The forward propagation is implemented as usual, so this is a regular symbolic execution step implemented in every symbolic execution machine. So we just take state and propagate it if the path condition is satisfiable. And the new thing is the backward propagation. So as we have already told, we just compute the weakest liberal precondition, we calculate the correct level of this, and we propagate back to the starting point of the new state. So essentially we do the thing that was shown in the picture before. So by interleaving all these steps, we get some new pretty flexible strategy that allows us to reach something that can be reached by the existing approaches. So this is, for example, one case where the forward propagation and backward propagation in isolation alone will fail. I will not go through the details here, but the forward propagation might, when it gets into this point, if it does not guess the correct values of n and k, then it will be stuck in this while true loop. While backward propagation can go, yeah, so the target is do something. If we propagate this do something back, we can successfully skip this while true loop. But actually, when it will try to get through this heavily branching on k code, unless it knows the requirement on k, it will stuck. It may stuck here. But the forward propagation knows that k is greater than 35, and then it will quickly go through this heavily branching k code on k code. So the idea is to conjoin the results, to conjoin the results of the forward and backward propagation, and this is what happens here. We also have tried some search heuristics, like using weighted random searchers and combining it with shortest distance based searchers. So we propagate the states which reach one target in the least possible amount of steps. And for some states and pops, we calculate just the CFG distance if they're in the same function, or otherwise append the call graph distance to it. And we start there is also one insight to start the isolated exploration in CFG joint points, because actually all these points are those the points where the backward exploration forks. And we speed up the, we also have tried to interleave the forward propagation searcher with targeted searcher to speed up the casual coverage mode. And we have implemented this in the tool that is called guided klee. In this tool, we have implemented our bidirectional approach with the targeted test generation mode. So it extends klee with the lazy initialization, it extends it with the weakest liberal precondition calculation, bidirectional symbolic execution, and those targeted searches that I've mentioned just now. But for now it is closed source, maybe it will change in future. So let me demonstrate it in action. So we have already run klee on this regex example, and it took 24 seconds. Right now I will try to oh, yeah, I'm in the wrong directory. So it managed to cover, let's see the statistics. Actually, it managed to generate 100% coverage, but it managed to do it in much more rapid manner. So here we just interleaved this targeted search with the regular test coverage mode, and we have executed much less instructions, so the number here was much more than this one. We did not stuck in loops, and that's why we even see that the most time, 90%, was the time where the solver was solving the path constraints. We have also evaluated it in the test.com benchmarks, and we get pretty encouraging results. So I think, I hope that a lot of people here understand these plots. So here we have just the point. It has two coordinates. One coordinate is the time taken by guided klee. The other coordinate is time taken by the regular klee. And a lot of points are in this part. So this means that klee works in average more time than guided klee. And still we have managed to obtain pretty compatible test coverage. Yeah, so I guess I'm running out of time. So I have also a part where I talk about the proving unreachability of proof obligations, but I think it's not that important. Thank you for attending me. Yeah, let me go to the concluding part. We've discussed the state of art of symbolic execution and targeted test generation. I have presented the bidirectional approach for targeted test generation. And we have some interesting directions for future work, like implementing this bidirectional approach into other symbolic execution engines. So if you have your engine and interested in implementing it, please contact me. We want to develop some more efficient bidirectional exploration heuristics and probably even use machine learning there. And also it is interesting to understand how to work with the concurrency. So how to block the proof obligations to prove the unreachability of proof obligations of the concurrent code more effectively than the existing engines do. So thank you again for attending me. I don't know if we have time for questions, but I will be glad to answer them.
Thank you, Dmitry. Colleagues, do you have questions?
I have one question. Thank you for your report. It was very interesting. The technology is very promising and very complicated. And my question, you have said that this technique has been successfully applied to large programs like operating systems. And how do you make this in reality? So this kind of systems consist of a large number of functions. Do you artificially restrict the depth to which this symbolic execution can go, and you apply this symbolic execution to every function in isolation, or do you get, or it is better to get one module and extensively or intensively apply the symbolic execution to this module?
Yeah, thank you. This is a good question. So here I tried to find the slide. For instance, I think you talk about this slide. So here, the Sage prover, as far as I know, is not modular. So of course they have implemented some summarization strategies, but what it does, it is just starting an entry point and tries to and leads the state up to the point. So if it sees the interesting point, it tries to forward propagate the state there and speeds up the repeated analysis results by inferring those function summaries. But so all these symbolic execution engines, as far as I know, perform this monolithic analysis, so they are not compositional. Yeah, then our idea is try to bring more compositionality into the symbolic execution by starting the points from the arbitrary points of the program and propagating the targets back. Yeah, so these engines do not do this, and still they are pretty successful.
Okay, thank you.
Dmitry, I have a very technical question. So you introduced the notion of weakest liberal precondition. Is it the same as just weakest precondition?
Oh, this is a very book question. Yeah, thank you. Not at all. If you see the book, you will note that the weakest precondition and weakest liberal precondition are just same unless we talk about the loops. So weakest liberal precondition is a bit more liberal notion because it allows the non-termination of the loops, while weakest precondition should guarantee something like that. Oh yeah, this is the notion introduced by Dijkstra, and he artificially split it, all those notions, meaning the termination.
So you mean that weakest precondition also assumes termination?
Yeah, as far as I know, yes. I'm not sure about those book details, but as far as I remember, there's something like that.
Yeah, I guess it's like difference in terminology, but for me, yeah, weakest precondition
here in this definition, actually,
exactly the same definition you showed. This is why I'm asking.
Oh, sorry. The remark here is that in this definition, we actually do not care about these details, because if we propagate some proof obligation through the state, this state has already been computed, so it is already a terminating branch. So here we might tell that we compute the weakest precondition as well. Yeah.
Thank you.
More questions?
I want to ask some terminological question. Can I?
Yeah.
Thank you for an interesting report. I want to ask about the terminology. You use the term lazy instantiation. Yeah. I'm confused about the term lazy. Why do you use this word? Why is it lazy? Could you explain a little?
Yeah, thank you for your question. So here, this is the demonstration. Here we begin with completely undetermined heap. So initially the heap has no objects at all. And this code does not instantiate any memory at all. So it just reads memory. It does not allocate some objects in memory. So why is it lazy? Because we discover the contents of this heap while investigating this code. So if we read some location, only then we instantiate this location in heap. In this sense, we get the laziness in the discovering of heap contents. So we do not require some preliminary preliminary initialized linked list given to this function. We do not require the a priori bounds on the sizes of these data structures. Instead, we just lazily unroll the structure while it is needed for driving, while just drive by our code investigation. Yeah. So this is why it is lazy.
Yes, I understood. Thank you.
Okay, let's thank speaker once again. Thank you, Dmitry.
Thank you again for inviting me.
And now we have short break, so-called coffee break.